Hi class, I just want to give you a few messages. It's July the 28th, Thursday. As far as your flashcards go, as you will recollect, for the first exam, we had gone through maybe flashcard 3. There were a couple reactions we hadn't done yet on flashcard 3. You should be doing 3, 4, 5, 6, 7, 8, and I believe you can do about half of 9, okay? Specifically, I was going to give you a little guidance about a few of these. Specifically on flashcard number 7, in position 8 on flashcard number 7, what you're doing in that reaction is forming a protecting group. Okay, and I wanted to talk a little bit about this because this seems to be a point of confusion for a number of students. This acid that's given here is a sulfonic acid, which is very similar to a sulfuric acid. There's a step missing here really, because it should say Mg ether, and then it should be followed up with acetone, which is this compound, and then followed up with H3O+. I'm bringing this up because a lot of people are asking me, when do you use a protecting group? This is a classic example of when you would use a protecting group. The problem is that the goal here is to make a chloro-Grignard or chloromagnesium compound, and then use that reversal of polarity to attack this carbonyl and form an alcohol, ultimately. But the problem is the molecule already has a carbonyl in it. Okay? Now again, this problem is on position, the fourth one down on the left column on flashcard 7. And as I said, I left that reagent out. Now, you have to work on this mechanism a little bit, but we've done this a couple times in class. Okay, so what you would do is the strategy would be that you would protect this group as a ketal, then make the Grignard, do the reaction, and then use acid to protonate the Grignard product and take the protecting group off. Okay, now again, why would you want to do this? Because if you made a Grignard in the presence of a carbonyl, the Grignard would attack other molecules like itself on the carbonyl position. So you want to block it, do the chemistry, and the chemistry will be, the protecting group will be immune to the chemistry, and then take it back off again. So to give you like an outline of this, because this is kind of an important sequence, okay, to make the protecting group would be something like this. And again, when you're working with your flashcards, you really should be writing mechanisms. And I know I've written this mechanism several times in class at this point, between review classes and regular class. It was covered in regular class, although I used a different alcohol. So let's say we've got this sulfonic acid. I'm just going to put an R group here. What's going to happen first? Protonation. Okay? Protonation of a carbonyl is an essential point, because protonation of a carbonyl results in the base of the carbon being more positive. So that's why I always kept saying in class, it renders the carbon more positive. If you get this protonated form of the carbonyl, you can draw a resonance form. This is one bond resonance, kind of in reverse. Is this showing up on the film? Mm-hmm. And then you would have this compound. Okay, what would you do next? You would take your alcohol and attack this carbocation. Okay, so you're making this into a very positive site so that this weak base will attack. It's very much like an SN1 reaction at that point. Okay, what would be the next point? I think I could do this a little faster here than in class. All right, and I've been saying in class, all you have to do is the next thing. So what's the next thing? This is a case where you do a proton exchange because you actually want to get this group off. So I've told you can do this abbreviation of a proton exchange just to save a little space when you're doing mechanisms. So you would get this, you'd have OH2 plus O. And someone was saying this looks like a praying mantis. I'm not sure if it looks like a praying mantis. Okay, this pops off as a good leaving group. I'm writing these as SM1s because I'm an acid. Okay, so now I've got the chlorine on. That has left. Okay, and then you would have this carbocation. Now this has resonance stabilization with that oxygen. Okay, so that's a stable cation. And people keep saying, why does the leaving group just leave? The leaving group just leaves because we are an acid, we don't have any strong nucleophiles, and we are forming reasonably stable cations because they're secondary and they are resonance stabilized. Then what will happen? This, particularly because it's intramolecular, will come together. Remember, this is very favorable from an entropic standpoint because you're going from one molecule to one molecule, where many reactions go from 2 molecules to 1 molecule. Okay, so when you do this, you're not changing the entropy that much. Also, you know, it's kind of sitting right there in close proximity. All right, so we have this. Then what you do is you take your water molecule or some solvent molecule and you pull that H off, and you'd have the protected halo compound, okay, and that's called a ketal. Okay, now once you get the ketal, okay, what are you going to do? I can't write this whole mechanism out because it would take forever. But if I really did add magnesium, and again, this flashcard, I left this off. I don't know why. But if I added magnesium and ether, you should all know what would happen. You would make the Grignard, and you'd reverse the polarity at the site of the chlorine. And what the advantage of this is that this group is stable to base. It's not stable to acid, but it's stable to base. So this is going to stick around while you continue to do the Grignard chemistry, which would entail taking this anion, attacking this, opening this up, so that you get this kind of structure. Excuse my geometry there, it isn't so great. Okay, and then you get this. Okay, now, when you add the acid, what you should assume is that you're really doing the mildest of operations. So if this had a double bond in it, the double bond wouldn't be cleaved by this acid. This would be kind of like it's sitting in ice and you're like dripping in some dilute acid. So one thing that happens is this gets protonated. How many minutes in am I?
7.5.
Okay, this gets protonated. I can go over, so don't stop me. Okay, so this gets protonated, and then where would I go from there? Well, you should be able to take this group off. All right, look kind of like this. There's an OH, and then we had this. Okay, you should be able to take this off with acid. If you add the acid, you just go the exact reverse. This is what I kept referring to in classes, the principle of microscopic reversibility. Okay, yeah, there's a lone pair there. You protonate this, and you kind of have to think to yourself, what do I do next, right? So what do I do next? I've made a good leaving group. Pop the leaving group off. Okay, then what do I have? Then I have a resonance stabilized cation. So there's resonance stability there. All right, what's going to attack? If you're in water, what's going to attack this is water. And I'm telling you, this is the exact reverse of what I just wrote. Like you could take, it's like a movie running in reverse. Except for the fact that I was able to do the Grignard. So I'm not going to finish this, but I want you to be aware, you know, we did go over this. It's not that complicated. Then what do? Then you do a proton exchange. You put the proton over here. You pop that off, and you will have, it becomes clear what this solution is. Sorry, this is messy. I'm trying to get this done quickly. But you will have this with a plus charge there, and that's resonance stabilized. And if you just pull the proton off, you'll have the ketone back. So again, the point behind this kind of protecting group is to block the carbonyl so that you could do some other kind of carbonyl chemistry. So where would this protecting group come into play? It could come into play in a Wittig. It could come into play in a lithium aluminum hydride reduction. there's a couple places where it could come into play. So, as I said in class, if you had, like, say you had some kind of structure like this, and it had a carbonyl in it, and you wanted to do some Vidic chemistry with this, like you wanted to convert this into a phosphonium ylide, okay? You can do that, all right, and then say you want to react this with something else, you can do that, but the problem is you've got to protect that first. And you could, because you don't want this attacking other molecules. Remember, you have lots of molecules. So this could attack a completely separate molecule of this, okay? So if you want it to attack a different carbonyl, you've got to put that ketal or acetal protecting group on and then take it off at the end, all right? The only other place you've seen protecting groups are sulfonates on aromatic rings. Now, other things in this, these sheets that kind of came up that were a little odd. So now I'm moving to 8. 8 is one that you should skip on sheet 8 is position 2. So this is position 1. Position 2, that's the Clemmensen reduction, and we haven't done that yet. The bottom is just normal Vidic chemistry. Again, we're only doing like classic Vidics in this course. As far as page 9 goes, I would say page 9, a lot of it is not on this test. So on page 9, you would want to do position 1, 2, 3, 4. When it comes to position 4, you should substitute for the reagent H2, it should say H2CrO4, that's the typo. Okay, then you should do position 5, you should be able to do 6, and that's about it. Okay, the top of the sheet is all really kind of a review of how to make carboxylic acids, or how to do oxidations. It's really a review of how to do oxidations. The last thing I want to say about these sheets is that, I should say one other thing about flashcard number 6. Down on the bottom corner, lower left corner, there's a reaction with a reagent, trimethyl